and Hilbert are those that you see over here. The one that was presented in Berlin in November 25, the one that was presented in Göttingen in November 20. It's not very difficult to see the equivalence between them, but just let me remind you things that appear here. The reachy tensor, we have it over here. The stress energy tensor, the trace, of course, the metric tensor related or acting as gravitational potentials, and a constant. And the interesting part of the story, or one of the interesting parts of the story, comes when we realize that there are not only two equations that we have to consider as part of the story, but there is more, because what we see here are the published versions. One, Einstein's, was published quite soon in December 2, which is the one that we know. And that wasn't, there was, the equation by Hilbert was published in March 6. This is 3 months after. These proceedings usually work very fast, but still here it's like 3 and something months. And there is, we know, a different version of Hilbert equations. We know this because of this document that you see here. So this is the published version, and this is the correcture, or the galley proofs. And this is a well-known story that I have been involved with, that I found this document in the Hilbert archive. And the interesting part about this document is that it has very clear over here a stamp saying that this is from the 6th of December. Hilbert may have seen it even before. Therefore, anything that we see here is closer to what Hilbert presented in the talk than what we know from the published version. I will talk about this, of course, but here you see the stamp very nicely. And the thing is then that we have an earlier version of Hilbert's equation, probably very close to what he showed there at the time, presented in his talk, and which is not exactly this one. Of course, we can go from this one to this one, but people who are interested in the question, who had the explicit, correct, etc. equations first, then has to relate to these 3 equations and not just to the 2 that we saw before. So when I found this document, we then published this article in '97 together with Jürgen Renn and John Stachel, and saying what we said about the process that I will also say some words about it, the process whereby Hilbert saw eventually the equations published in Einstein's paper, and he made some changes. And I want to say from the beginning that nothing like plagiarism or things like that. I usually don't care about those matters, except if there is something very flagrant here. But this is just, you know, we all publish papers, we change things. And I think that Hilbert, and I know precisely, he never know that historians in the 90s would be interested in seeing exactly what line is there or something. And hence, I want to say that the question, who arrived first, I'm not going to say it's not interesting. It is, we're all curious about such things, but it is not the real interesting issue here. The real interesting issue is, as I wrote in my abstract, is this part. Einstein meets Hilbert on the way to general relativity. And it is interesting because we have 2 scientists, of course, both very prominent, and of course, looking back, extremely prominent, but they meet at some point and they have their interaction and the conversation and their misunderstandings, etc. And this is what makes this story so interesting and, in my view, so important for the history of the early 20th century physics and mathematics as well. So I will talk about that. And the second question, or the little question who arrives first, it's part or derives from the larger story. So let's start from Einstein's way to general relativity, which is not the part that I really investigated in my works. And we have here John Norton, from whom at the time I read in order to understand what was going on over here, I thought that I would never be able to understand this complex story and this complex physics, but thanks to him and to others, I think I more or less understood what's going on the side of Einstein. So let me tell this very briefly before I go to the part that I can really speak a little bit more about my own take and my contribution to seeing this. But of course, this is a central part of the story. So specifically, Einstein's way to general relativity is Einstein's way from special to general relativity. And the idea that the principle of relativity may, depends on the idea that we have, be generalized to work on systems of reference that are not inertial with respect to each other, but are more general and possibly generally general. So this was one of the questions that was that had to be addressed. And we know that Einstein from very early on started with some early attempts to generalize the principle of relativity, but he didn't, in the end, didn't pay much attention to this. He had other things that at the time were more important for him, except for one point that was very important here, which is the principle of equivalence, which he defined as the most fortunate thought of my life. And the idea is, you all know it, I guess, we have in Newtonian physics, in Newtonian physics, the mass appears in two different but related contexts. In the context of the second law, in the proportionality between acceleration and force, and at the same time in the in universal gravitation that describes a law that depends on the masses of the two bodies that attract each other. And in classical physics, we have the fact that they are one and the same thing, or they are equal. But for Newton, sorry here. But for Newton, this was a puzzling fact, and for Einstein, it became a basic principle. I will skip this over here. And so we know, as I said, I will return to that immediately, but as I say, there are early attempts in 1907. In 1908, we know that Minkowski came up with a draft of a relativistic gravitational theory. At this time, he started to formulate the theory in terms of four-dimensional four-dimensional formalism, and he thought at the time that he would be able to use this formalism to come up with a theory of gravitation, a relativistic theory of gravitation. It had some problems, but it was a nice attempt. And only in 1911 and 12, Einstein returns to his attempts to generalizing relativity. At the time he was in Prague. There is the very important idea of the rotating disk. This is an idea that Norton and some of other people and collaborators have stressed very much. And it's really important because the point with the rotating disk is that if we take a rigid disk, we know that the length of the circumference is 2 pi r. But then we know that if the disk starts to rotate, then we can consider it in terms of special relativity. And if we have let's say, a uniform angular speed, then it is clear that this linear speed at the outer part of the circle will be greater than that in the inner parts of the disk. And hence, according to special relativity, the contraction will be greater. And hence, the idea of a universal, let's say, universally valid formula for the length of the circle becomes problematic. So that Einstein quite early on, even though he at this time he was very far away from starting going into the theory, but he already know that something with the geometry had to change here. And then the continuation of the story is when he comes to Zurich and joins the university and meets again his old friend, Marcel Grossman. This is very important because Marcel Grossman was a representative of a very important tradition, partly we can say from Switzerland, partly from Italy, of the calculus of variations, Riemannian theory, Riemannian geometry, all kind of things that of course became fundamental for Einstein. And I think that many times this is, this is taken for granted. Well, he knew that there was some problem with the geometry, or we have to treat the geometry in some special way. And then there was the non-Euclidean geometry, and he did that. No, well, sometimes you need some contingencies in history. And here you had the very inadequate one, that he came to a place where he had a good friend, a mathematician, and this friend, a mathematician, was a big expert exactly in what he needed for doing his research, or for the mathematical part of it. And well, it doesn't mean that if he had moved to, I don't know, some other place in Europe, he eventually would not have come to it, but here he came to it thanks to the specialty that Marcel Grossman represented. So, and in these years, there is a very nice process. Again, John Norton described it a long time ago, in which Hilbert had to mix Einstein had to mix certain considerations in order to reach the general theory of relativity. So there was the equivalence principle, there was the Newtonian approximation in the sense that Newton's laws gave very good results, and any other theory that wanted to compete with it had in some sense, and it's to some extent, to have in the limit, let's say, or converge to the Newtonian approximation. It cannot be very different from that. And of course, there was the desire to reach a general covariance. And this could be done with the mathematical tools that Grossman offered him, taught him, worked with him, etc. And what happened during these 2 years, that things not always fixed with or went well with one another. There were also, of course, important physical principles like causality and other things. And Einstein was trying to work out his way in all these labyrinths, let's say. So there are two very important articles. The first one is the Entwurf, the draft of a generalized theory. And then there is another article in October 14, where Einstein presents the idea of the whole argument. And I would say very briefly, the interesting thing about the whole argument was that that Einstein realized or thought that there is a problem with general relativity because there is a conflict with causality, coordinates, again, all kinds of things that John Norton has explained very clearly. And the interesting thing for me is that he said, well, I'm going to generalize my theory, but it won't really be generally general. It would be quite general, but not because I see difficulties and so on. And part of the process that leads from what happened, let's say, in 1914 to 1915, was that Einstein understood what was the problem with the whole argument and overcame it, partly because of his interaction with Hilbert and so on. So, there is, I need to mention this, the Zurich notebooks, because this is a very interesting document that historians like Norton, Jürgen Rehn, Michael Janssen, and all these people who have done this wonderful work, they went through it. And we see here how the ideas of Einstein evolved and where he had new ideas, new notations. Is very interesting. I don't have time to go into all of this, but if you, even without being a real expert in the history of general relativity, you see things. I always like to see here, for example, that he has the summation that he then gives up and makes things more clear and all kinds of things like that. So we know a lot about what happened with Einstein in these years. Another very important thing to mention here is that, especially in 1914 and 1915, Einstein was not working alone. He was in a very important interaction with other physicists that came up with their own theories, their own ideas, Sometimes they fitted together with those of Einstein. Sometimes they were opposed. And this helped very much Einstein to sharpen his ideas. There is also here the mathematician Tullio Levi-Civita, who was an expert in tensor calculus, etc. And he pointed out some difficulties in Einstein's work. And all of this is important because it's important to understand that we have this community of people working together, criticizing each other, sometimes in a more friendly way, sometimes in a less friendly way, but always the idea are there. And I think that the dialogue becomes fundamental for the progress that we see here in this year. And then Einstein comes to Göttingen, a very important milestone in the history. You probably know that Göttingen was the mecca of exact science at the time. And I take the trouble to put all these pictures over here because those of you who don't know and don't know the name or don't remember exactly the name have to see the extent to which we are talking here about a community that included the most important, the most brilliant people, some of them coming to visit. I could go through the names, Born, Ehrenfetzer, Melo, Curran, Schwarzschild, De Baye, and many other interesting people over here. And of course, for Einstein, this was a very important opportunity to present his ideas. In Berlin, he had less people to talk to about all of this. And he knew that in Göttingen, things would work out better. Of course, since we were in the war at the time, they were in the war, not all of them were there. Actually, Caratteodori, Eminete, Runge, the De Baye, and of course, Hilbert and Klein were there, and they were a very good audience for him, but not bad. And from the point of view of Einstein, this was a great success. He wrote to Sommerfeld in Göttingen. I had the great pleasure of seeing that everything was understood down to the details. I'm quite enchanted with Hilbert. That's an important man for you. So in November, there is an intense correspondence between Einstein and Hilbert. This has been analyzed for a long time. I will not go into it, but this is exactly where we can see the details of the interaction between them. And then, as I said, he presented the equations. As he said to Sommerfeld, I had one of the most stimulating times of my life. So this gives us an idea of Einstein's way to general relativity. We can talk about that later if necessary, but I think that the main lines of the story are very clear. And now I want to come to Hilbert's way to relativity, or more precisely to this talk that he presented in Göttingen, Die Grundlagen der Physik, the foundations of physics. And we have to start from there to see that he was not aiming at the same place as Einstein, even though they somehow reached the same place. And I will talk now about his way. And his way starts at a very different place. No, I want to say also that his way was not just a chance that or a coincidence that he came here. I have all the quotations that say, you know, like Hilbert jumped on the bandwagon of success of Einstein's theory, or many things like that. But when we read more closely what he wrote in the article, and especially when we see all of his career in Göttingen and before Göttingen even, then we see a very different picture. No jumping on any bandwagon and nothing of the like. So we have to start here in the list of problems that Hilbert presented in 1900 in the International Congress of Mathematicians, a very famous list of 23 problems that many of them occupy the minds of the best mathematicians during the 20th century. Some of them are still open. You can earn $1 million if you solve it, for example, the Riemann conjecture and so on. And there is the sixth problem. The sixth problem says to treat in the same manner by means of axioms those physical sciences in which mathematics play an important part. And very much like the participation of Hilbert had been for many years considered just a jumping on a bandwagon of success, so this problem was considered always to be a marginal one. For example, to bring you a very well-known quotation, the honor class, which is about the problems, it would seem that Hilbert overreached here. Well, I didn't think that when I started to work on this, and I wanted to understand what is this problem, and indeed, what is the axiomatization of physics that Hilbert had in mind. So I came up in the end with the conclusion, and this is the way that I can see the Hilbert's way to general relativity. First, that physics was a fundamental pillar in his scientific worldview. Second, that the sixth problem continually engaged his efforts. Indeed, it is the only problem out of the 23 to which Hilbert continued to devote efforts all his life. The others either were solved or didn't interest him anymore. This is the only one that he continued to work in. And the thread that goes through all of this is the idea of the axiomatization of physics, about which eventually I wrote that book, of which my talk today is just a part. Now, there is a difficulty in understanding Hilbert, and this was the one that I had to overcome in order to see what's going on over here. Hilbert published in 1899 the famous book, Grundlagen der Geometrie, the Foundations of Geometry. And often there is one sentence that he said, not in the book, by the way, but he said it, that it should be possible to substitute point, line, plane by chair, table, and beer mug in the book, and all the results of the theorems will continue to be valid. This is one thing. The other thing is in the 1920, he started what he called the Affinities program for the foundations, or for proving, for the foundations of arithmetics, and more specifically, for proving the consistency of arithmetic with Affinities tools. And the word formalist was used later by von Neumann, not by Hilbert, but these two things put together led for many years to the idea that Hilbert was a champion of formalism in mathematics as well, not in formalism as a tool to prove the consistency of arithmetic using Affinities methods, but that Hilbert was a formalist, that Hilbert's axiomatics is an axiomatic formalism. And just to give you a very important example where this is said, we can take Jean Dieudonné, one of the most important members of the Bourbaki group in France, who consider themselves to be the real heir of Hilbert. They said it everywhere. And they say, they put forward this picture of Hilbert as if for him, mathematics was as a game of chess. Hilbert does not speak of mathematical truths, but rather of correctly following rules arbitrarily stipulated in advance. And nothing can be farther away from what Hilbert, the way Hilbert conceived mathematics, not in the specific problem of the foundation of arithmetic, but as in general, and the strong connection with physics. So we have on the one hand, Grundlagen der Geometrie, and we have Grundlagen der Mathematik, which is of arithmetic. And then we have in 1916, the Grundlagen der Physik. So it didn't make sense to me that Hilbert could have been a formalist in that sense, because it didn't make sense to me that that was the case for geometry to begin with. I couldn't believe that this was Hilbert's conception of geometry, but maybe. But if he's a formalist of that kind, what is the meaning of this article, the Grundlagen der Physik? And I said to try to understand it in the context of all this idea of Hilbert and physics and the axiomatization, etc. So I want to give you two quotations by Hilbert. Basically, I have been giving these quotations for the last 20 years whenever I speak about Hilbert, because it gives you a very clear idea of what is in his mind, what was in his mind when we spoke about the axiomatization of physics and axiomatization in general. So the first one is of 1919, so very close when he started the Affinities problem. He says, "We are not speaking here of arbitrariness in any sense. Mathematics is not like a game whose tasks are determined by arbitrarily stipulated rules. Rather, it's not arbitrary. It is a conceptual system possessing internal necessity that can only be so and by no means otherwise." And if we try to understand in this context what he did in physics, so I go to my second quotation, which is taken from one of the lectures that he gave. Of course, this was the fundamental material of my research, the many courses that Hilbert gave in Göttingen, in mathematics and in physics. And he has his student, we don't have such things anymore, at least not here in Israel, a student taking notes of everything you said, and then it becomes the textbook of the book. Certainly not if the student is, let's say, Max Born, who particularly wrote this or took notes of this course. Look what he says here. This is fundamental. The edifice of science is not raised like a dwelling in which the foundations are first firmly laid and only then one proceeds to construct and to enlarge the rooms. Science prefers to secure as soon as possible comfortable spaces to wander around, and only subsequently, when signs appear here and there that the loose foundations are not able to sustain the expansion of the rooms, it sets about supporting and fortifying them. This is not a weakness, but rather the right and healthy path of development. So for Hilbert, axiomatization comes in the end, when the theory already exists and is there, and we know, especially in physics, we know the interaction between theory and experiment or observation. And he says, of course, that for him, the most important example is geometry, which for him is an empirical science, not formalist, it's an empirical science. And the next one in turn is mechanics. Why? Because we know geometry more than we know anything else. We knew mechanics at the beginning of the 20th century more than we knew anything else except geometry and so on. This idea is that with an axiomatic analysis, we have created and clarified the logical structure of the theory. Then, if there is some problem of coordination between theory and observation, then we don't need to throw the theory. The theory may be okay, but we have to correct it a little bit, okay? He says this also very clearly in a letter to Frege. This letter is very important, or this correspondence, because people who study the history of logic try to discern what Hilbert had in mind, Frege had in mind, but I see it very important for the history of physics in the sense of understanding what Hilbert had in mind. Because he says the following: after a concept has been fixed completely and unequivocally, it is, on my view, completely illicit and illogical to add an axiom, a mistake made very frequently, especially by physicists. And he had in mind the problem at the time with kinetic theory, where there were many questions because things didn't fit together, especially not the Newtonian determinism with the probabilistic calculus. Something didn't work out for him very clearly. And he says physicists discover a new principle and try to introduce it, but they didn't. I mean, the way they do it is to speak about the plausibility of the principle, which is okay, but this is not enough. You have to see how it fits with the mathematical theory, okay? And well, I could go on and on with this. I think it's very important and interesting, but let me tell you that in 1905, then, this course on logical principles of mathematical thinking is fundamental for understanding what he did later, because he devotes chapters to mechanics, thermodynamics, probability calculus, kinetic theory of gases, insurance mathematics, electrodynamics, and even psychophysics. He tried to explain what he had in mind when he spoke about axiomatization. Let's be clear, what he does for mechanics is not exactly what he does for psychophysics, which is giving a direction of what can be done. But remember, in the late 19th century, there is this very important German tradition of psychophysics, and there was the law of Weber, Fechner-Weber, and so on. So there was something to speak about, but still, we see here what he's trying to do in the sense. Also, very important to understand, when Minkowski works on relativity, I don't have the time, of course, to go into that, but it's important for me to tell it, that if you take this very important article, which I already mentioned, in which Minkowski presented the possibility of extending the principle of relativity to work on gravitation, I read this article as an attempt to apply the idea of the axiomatization of physics. I have written about it, and you can read it if you want. The idea being the following: okay, we have now the principle of relativity, but we have here mechanics and thermodynamics and electrodynamics and so on. The principle is plausible, but does it really fit the edifice of mechanics? Does it really fit the edifice of thermodynamics and so on? And this is what he does in that article. Well, unfortunately, of course, Minkowski died in 1909, so he didn't continue to work in this, but we can see they were, as you know, they were very good friends. They were working together. There has been a lot of historical research about this, but I think that by putting the focus of the axiomatic program of Hilbert, we earn a lot in understanding also Minkowski and physics. So at a certain point, Hilbert starts to expand his physical horizons between 1909 and 14, especially, not only. And he worked and also published, but there is a very big difference, a gap between the kind of things that he's working and thinking about and what he published. Hilbert published relatively little compared to what all he did in his courses, and you can go through his courses also in mathematics, but also in physics, which he always taught 4 courses every year, 2 on mathematics, 2 on physics, always in the cutting edge of what was going on and almost never repeating. You know, we are teachers today and we know what is to prepare a course. He was always advanced seminars and courses on the cutting edge of physics and of mathematics. So he worked on kinetic theory, radiation theory, and most importantly, on structure of matter, electron theory. And also there is a very important thing about this, that is his passage from mechanical to electromagnetic reductionism. The debate since the late 19th century and the beginning of the 20th century between these 2 camps, there is also the energetic camp, but the real 2, the big ones are mechanical and electromagnetic reductionism. And Hilbert was in favor of the mechanic reductionism, but at some point he said, I say it very schematically, but believe me that this is more or less the direction, say, the mathematics becomes so complicated when we believe and try to implement in physics the mechanical reductionist or the mechanical reductionism, that it cannot be true. I go to the electromagnetic reductionism. This is in 1912. And this is very important for the story of relativity. Again, I want just to tell you that all this time, you know, Hilbert is in the cutting edge of mathematics, right? Theory of invariance, algebraic number fields, foundations, integral equations, and also physics is part of this. But the structure of matter becomes the real focus of his interest in physics. He started to have assistants, like the Bayer was his assistant, Hertz, Landé, all kind of people who became very important. The idea was that they should bring him every week the latest publications, you know, of the physicists in the world, and tell him, look, you have to look at this article because it's very interesting, it's very important. And he said, why? Explain me. Okay, and then he got the idea, and then there came this stage of the Nostrifizierung, which is take those ideas and put it in the context of how we speak here at Göttingen and how we do things here at Göttingen. So what happened with general relativity is not different from other things that happen here. And in the structure of matter, he has this seminar running from 1913, 1914. It later it was called the De Bayer Seminar, but it was Hilbert Seminar in the beginning. And this is the place where everyone working in quantum mechanics came to explain. This is where Bohr came, and Sommerfeld and Pauli, everyone. That was the place. For Neumann as a young student, and then he published the article on the foundations of quantum mechanics and so on. Now, in 1912, 1913, Gustav Mie was not a very prominent physicist, but he was a good one in Germany. He comes up with this electromagnetic theory of matter, in which he wanted to describe the electron as part of the ether, as a singularity, and not opposed to some kind of mechanical reductionism. And he had many interesting ideas that became the basis of Hilbert's theory. But in order for that to happen, it had to go through the hands of Max Born. Max Born was very strongly influenced by Hilbert all along his career. And he understood that there are interesting ideas in Mie's theory of matter, and he reformulated the theory in tensorial terms. And also in tensorial terms that are quite abstract, in the sense that you have 4 variables, not necessarily referring to electromagnetic or electromagnetic magnitudes, even though it can be, of course. And this was very important, and Born knew it, that this was the way to present things to Hilbert. A theory of matter that can be extended for all of physics, for all the physical phenomena, including gravitation, and also that the mathematical formulation is a very good one, is a very clear one. And at some point, they started into that to put or to import the ideas of Einstein's theory, because in the tensorial context, it was very nice for them to adopt, you know, the stress tensor, and especially, I would say, which was not part of Gustav Mie's theory, the G mu nu tensor, right? To see that he can connect all of this with the gravitational problem or the gravitational issue. So Born was able to translate this theory in a way that would appeal strongly to Hilbert. And this is when we come back to the meeting of these two people. So you see that it comes from the idea of the axiomatization of physics, the focused interest on the question of the structure of matter, the idea that there has to be some kind of electromagnetic reductionism to this theory of matter, and then the ability to connect it to what he saw that was happening inside Einstein's theory. So that when Einstein came to Göttingen, Hilbert was enchanted with that. And they started their conversation and so on. From what we know from the letters, it was very friendly. The correspondence is very interesting because sometimes it was twice a day that they interchanged letters, like emails at the time. And it's very interesting to see how fast the mail worked. And also in the envelopes, you can see Herr Geheimrat Hilbert Göttingen. The mail, the post person didn't need to know what was the address because probably, I don't know, everyone knew Hilbert. Anyway, the interchange is very interesting because you see that sometimes it helps to each other and sometimes they read past to each other. Like he's talking about one thing and the other one is talking about the other thing, and they don't necessarily connect in all points. But each of them takes something important to his own view as his own take of the program. So we arrived to the paper, and just to give you some ideas, Jacob, perhaps you will see here things that you want to speak about them or ask me. This is presented in an axiomatic way, okay? So the first axiom, it says, I take Mie's axiom of the world function. This was not exactly the function that Mie had in mind, but the idea is to present a variational argument for a Hamiltonian function that has 10 gravitational potentials. That was the word that I forgot, the gravitational potentials G mu nu, and their derivatives, and also the 4 electromagnetic potentials and their first derivatives. Remember, Hilbert was the great master of the variational calculus. And much of what he does in his axiomatization of physics, mechanics, and so on, has to do a lot with variational calculus. So this is the way that he wanted to present his theory over there. And then there is a variational argument, as I said, and there is also an axiom of general covariance, okay, that he thinks, let me be honest with this, the axiomatic structure of this article is not of the kind that we find in the Grundlagen der Geometrie. Things are not so clear, things change all the time, but still, this is his way to say, look, I can do this thing over here, and I can present a foundation of physics that goes from the atom or from the electron to gravitation with the same language, the same situation, and so on. So there is an axiom of general invariance, and the Hamiltonian is composed by a gravitational part, an electromagnetic part. All of this is detailed in the article. Now, basically, if we look at the proofs that I mentioned, this is the equation that appears there, right? This is not the second equation that we did. So Hilbert was very close to the equation, but was not really there. And again, I think it's not that important because being so close, you know, then he sent his ideas to the print, the Gaelics came back. Meanwhile, he had read Einstein and said, well, this is wrong, or this is not explicit enough. I'll write it explicit enough. And you will see very clearly that he nostrifiziert, not in the personal or plagiaristic point of view, where he gave full credit to Einstein. He nostrifizierte in the conceptual sense. So
I'm sorry to bother. What does the bracket notation there mean?
The bracket is indicating the Euler-Lagrange solution to, or the equation that arises from applying the variational principle. Okay?
Right. So that will spit out the Einstein tensor.
Yeah, but he didn't. Yeah. He didn't do that. He didn't spell out. That's the entire thing. Okay. You see, and you know, when you spell out, you have to work hard. You are not yet there. You have to work. But then he saw eventually what Einstein had done, and he said, oh, okay, I can derive the same thing or in the same way. And then this is the equation that he saw, right? In December 2, someone brought it to him, of course, one of his assistant boys over there. And then he corrected many things. This is why we receive proofs to correct things, right? This is the idea. And he corrected, and you can see it here. I hope you can see it. For example, when he speaks about the gravitational potentials, he says, von Einstein zuerst eingeführt. Okay, Einstein is the one who introduced these potentials, and he changed the entire first paragraph because he first said, I have here the ideas of me, and then I use the methods of Einstein. But in the published version, he says, no, I start. Okay, he said, die gewaltigen Problemstellungen. No, this is not the one. He puts in the center the ideas of Einstein. This is the great thing. And I can give you more, even what for me is even more interesting than this. As I said, Hilbert was always teaching, in the cutting edge. So in the course that he taught in 1916-17, in the fall semester, winter semester, the course was not called, the course was the Foundations of Physics, but he devotes the most of it to the general theory of relativity. And he calls it very clearly Einstein's general theory of relativity, the greatest achievement of the human spirit ever. This is what Einstein thought in 1916, perhaps at the beginning of 1916. So all of this story the story is long. And then, by the way, we were accused, it was mainly me and other people, because there is a part lacking in the proofs, so that we came in the night and we cut it off, and all of this to say, we, the Jews, wanted to say that Einstein was the real creator of the theory and not Hilbert. But this is complete nonsense. And again, I wrote this book about Hilbert and the somatization of physics. If it was the other way around, if it was Hilbert, I have to change 3 pages in the book, which is 500 pages, because the real story is what I tried to give you an indication of. And what happened those days? Well, such things happen, and it's interesting. But another interesting thing, I will try to finish very soon because I see that time is running. So I will say a couple of things to round up the entire story. We know, again, Norton may say more about this if needed, that when Einstein at the beginning, March, I think, 1916, he published a systematic presentation of the theory for the first time. Remember, the other things were in the academy, it's a short presentation. There is a manuscript of an unpublished chapter of this long article, in which Einstein presented the equations in a variational form very close to that of Hilbert. But in the end, he decided not to publish. Probably he didn't want to give a lot of stress to Hilbert's approach. But we don't know. We just know that it exists, and it was not. Also, it's interesting, again, I just give you a hint. Einstein and Weil, Weil was the most famous of Einstein's many, many important students. So he was a real star. But there is an interesting Oedipal relationship between Weil and Hilbert. And at this time of their career, even more. And we know, like Einstein and Weil were laughing a little bit about Hilbert. Hilbert's assumption about matter appears childish to me, in the sense of a child who does not know any of the tricks of the world outside. And he's referring to the fact that Hilbert comes to physics from an extremely purely mathematical point of view, right? You have a variational principle, you have mathematical assumptions, and Einstein, he appreciated it, but not that much, probably. We also know in 1918, Weil presented his book, which is a good book until today. You can see it. Here is the place where people start to present systematically the theory. We also have to mention Pauli's book, which was a chapter in Klein's encyclopedia. Klein asked Sommerfeld, who was his former student, he told me, why don't you write this chapter, general relativity is going on. He was a young fellow writing his PhD, and then he came one day to Sommerfeld and showed him the text, and Sommerfeld couldn't believe, because it was a perfect presentation of the theory. It appeared as such in the encyclopedia, and then it became a book. But Klein told him, look, in your article, you cannot but mention explicitly Hilbert's contribution to this field. And indeed it is mentioned, but it's interesting to know what would have happened had not Pauli mentioned it. So Hilbert was mentioned especially and prominently here, but then in the history of general relativity, he, like his person dwindled a little bit, like, yeah, he just a mathematician who, yeah, he was very good in mathematics, and then came Einstein and told him, look, I have this problem, why don't you help me? And then he solved the equations and so on. No, that was not the case, as I hope to have shown here, and of course in what I have published about this. So to conclude, as I said, Einstein beat Hilbert on the way to general relativity. Who arrived first? Interesting, arises curiosity, but it's not the main point. The main point is how these people met, what happened with them, and the very nice expression, zwei wirkliche Kerle, two very nice fellows which appreciate each other, understand the magnitude of the achievement of each other, and know how to give the credit to each one when necessary, even if at some point they had an ill feeling about what had happened. I hope to have explained here this point of view, also to some of you who have heard, who hadn't heard, and here it is the story. Thank you for the attention.
Let's give a round of applause to Leo for a beautiful, beautiful talk. All right, questions away.
I just another quick notational question.
Yeah.
Capital K in Hilbert's field equations, is that the reachy tensor?
Yes.
Just a different notation.
I think it is a version of it. I don't remember at the moment. You remember, John? It's not exactly the same reachy tensor that Einstein uses, but this is why I say that that there is an equivalence between these two things, right?
Right.
There is a tensor of which you calculate also the trace, and you multiply the trace by the gravitational tensor, right? So you see that it plays the same. It may be exactly the same one. I don't remember, because let me tell you something, that all this game with the tensors at the time, it's a little bit complex, because things in Göttingen, because of the oral culture that they had, sometimes they were working with some assumptions and with some inaccuracies that filter in all the time. And many things, they use them. And then I know it's for probably for the reachy tensor. At some point, someone asked, are you sure that the reachy tensor has all these properties that you always say that it has? And then they say, we're not sure. Why don't you prove that? And so I think this is very interesting in itself, because it's a very different culture from what we are used to. And the same what I said about the article, that there are many inaccuracies in this article, and also the axiomatic analysis. We identify Hilbert with the axiomatic formalism. We think of it a little bit like Russell's Principia Mathematica, kind of. No, that was not his style, and it was not his style in physics, even less. Sometimes, I knew better the mathematical part, and I saw how he proves in number theory and so on. And then I read some of the articles in physics, and I said to myself, I think that if I sent an article like that to the mathematician, they wouldn't have accepted it, right? Because there were so many imprecisions. But I think it's important, because they did so many important things, and eventually someone proved and completed the details and so on. So this plays the role of the reachy tensor, or is exactly the reachy tensor.
Thanks. I had one other quick question. Oh, I'm sorry. I don't want to.
No, there's a raised hand system, but go ahead, Jacob, because you already had the floor. So go ahead.
No, please. I'll go to the end of the line. Sorry.
Okay, John, why don't you go ahead?
Sure. Can you hear me? It's coming through?
Yeah.
Okay, great. First, Leo, I just want to thank you for not just a wonderful talk, but a wonderful research project. I mean, this has been so illuminating. You know, I still remember when you told me, oh, we've found the Hilbert proof pages. And I remember thinking, oh, that's interesting. We might get a few little footnotes here or there. I had no idea that this would explode into this enormous productivity. So there's lots to be found from this, and there's something that you didn't have time to go through that I think remains important today in what happened here. That if you'll forgive me, I'd like to recount a different part of the story because I think it has important ramifications still today. So I know many of you know the story of the whole argument, but for those of you who don't, let me just tell you quickly what was going on at the time. Einstein in 1912 and 13 had failed to convince himself that generally covariant field equations for general relativity would be physically acceptable. And he produced the whole argument, which was an argument against the general covariance of any physical theory. The way it worked, and I'll give it in modern language, because that'll be important. The way it worked was that he identified diffeomorphisms as a gauge freedom in a generally covariant theory. Now, when you have a gauge freedom, you know you can't pin down the way the gauge quantities are going to evolve. And so what Einstein found was that if, for example, you fix the metric field everywhere, excepting a little hole in space-time, then that gauge freedom remains undetermined, and so you can't get a full specification of the quantities inside the hole. Nowadays, no one worries about that because it's simply a gauge freedom, so we don't care. Einstein worried about that and used that as an argument against general covariance. So the question then becomes, what happened when he took this to Hilbert? Right? How did Hilbert treat this? Well, the key thing in those proof pages is that Hilbert accepted Einstein's version of the whole argument. So Hilbert certainly goes through the machinery of developing what we now see as general relativity. He has the Riemann curvature scalar as an action. He forms an action density from it. He varies it. He does all of that stuff. But then he says, oh, but we know from Einstein that generally covariant theory is physically unacceptable. We have to add extra conditions in order to get a non-generally covariant theory out of it, which is what he does. Now, what happens in the proof pages is he writes that out. So by the time the Grundlagen der Physik is published, there's no trace that had happened, other than an incredibly convoluted development, because you're writing out a major part of the paper, so the equations are very complicated. So why does this matter? Well, there's a question, the whole argument became a topic in just abstract philosophy of space and time over the coming years. And then the question became, how ought we to think about this gauge freedom of general relativity? And there are two traditions here. One tradition, to which I belong, says it's a physical matter to decide that this gauge freedom actually connects mathematically different presentations of the same physical situation. And it's a physical decision as to whether that is the case or not. You have to, you have to give physical arguments for why that freedom is a gauge freedom not to be taken seriously. Now, there's another tradition that says, oh, mathematically speaking, the two are the same. Therefore, it's not possible that they could represent different physical situations. And this is a debate that comes and goes and comes and goes. There's been a recent iteration of it just a few years ago. What this tells us is the following. If thinking that it's a physical fact that has to be decided upon, if that is some kind of egregious mathematical error, then it's one that Hilbert made. And if this is an error that can be made by Hilbert, I think we've got to start asking whether this really is an error or not. And so that, for me, is one of the most wonderful things that came out of your discovery of these proof pages. I'm sorry you didn't have time to show us more of the pages and all the bits and pieces there. Anyway, so that was a bit of a long speech, but because it still has resonance today. I thought it might be interesting to talk about it.
Yeah, thank you for that compliment, adding that to what I said. And there is a lot to say here about physics. There are the questions that came up with energy and emanator as part of the debate. Hilbert played an important role in that, even though, again, the credit goes fully to emanator. But this is a time there when there is a lot of intense activity and also a little bit of discussion about cosmology and so on. And a very important thing, or very, I don't know if it's important, but it's clear, and we spoke about this in the past, I think, John, how Einstein changed his view about the relationship between mathematics and physics in the aftermath of this episode. Because historians, I guess that most of you here are not historians, but there is this idea of the young Einstein, right? The young Einstein is the one that follows the very immediate physical intuitions, like, all the stories about special relativity and the thought experiments and so on. But then when he moves, after 1917, I would say, he moves into the cosmological questions and the unified field theory and all of that. That is more in the style of Hilbert's mathematics or mathematical physics than it was before. And some people say, well, this is what spoiled Einstein and so on. Well, this is a matter of judgment. But a matter of fact is that there is a big difference between the Einstein before and after his encounter with Hilbert. I think this is also an important point.
Thank you, Leo. I would like to move on. We've got a couple of hands raised. One by Jacob, Peter. So Jacob, I'm going to put you second after Peter because you've already been through. Peter, go ahead, please.
Hi, Leo. I was wondering, or John, to what extent do Einstein and Hilbert begin to discuss a more geometrical interpretation of what they're doing? How soon does geometry enter explicitly into the discussion?
I will say about Hilbert, and then you can say about Einstein, John. You know better. But I think that in that part of the story where Hilbert is really into the theory, what we call the geometric approach doesn't show up very much. It shows in Weil's book. This is, he is the one who comes up with the idea of the purely geometric engaged theories and so on. I think that the connection that Hilbert sees is a connection that is more general, certainly methodological and so on, but not in the sense, I think, of what we later will become the geometric interpretation of general or approach or whatever to general relativity. What do you think, John?
Yeah, let me say two things. The first thing is that there's part two of Hilbert's paper, and in part two of Hilbert's paper, he lays out very clearly the conditions of physical significance. In other words, we would now say, oh, he just says the diffeomorphic fields represent the same thing physically. But he gives three different ways. It's a very careful development. He gives three different ways of determining that. One of them is you have an invariantly defined coordinate system, and I don't remember what the other two. That was the first thing I wanted to say. The second thing I wanted to say was, it's interesting, Peter, that you asked when did they come to a geometrical conception? And at this point, I want to put Dennis on the spot, because Dennis Lemkill, who I see is here and has a hand up, is the expert on this. Dennis, will you give us a speech?
If you want me to.
I do.
Yeah. I would say Einstein never really subscribed to the geometric interpretation of general relativity. So when I agree that, in a sense, that what we would today call the geometric interpretation of GR rests much more on Weil than on anybody else. Weil's introduction first of a generalization of Levi-Civita's concept of parallel transport, so Levi-Civita 1917, Weil 1918. Before that, it wasn't even conceivable to think of the Riemann tensor in the way that we do today, as via parallel transport and a very, graspable notion of the curvature of space-time. And when Einstein was presented with this new geometric way of thinking about the mathematical objects that he had used in the construction, he did not say, oh my God, this is all so beautiful, wonderful, finally a full geometric picture emerges of how to think of the Riemann tensor, of how to think of the Levi-Civita connection, of the Christoffel symbols now, clearly a geometric object too. That all of that doesn't really hit him. What he likes is that finally Weil shows that the affine connection is a object in its own right that can be thought of independently of the metric, which hence opens up all types of possibilities to generalize the mathematical foundations of GR. But when then, especially in the 1920s, partly based on Weil's very strong geometrical rhetorics, philosophers like Meyerson and others want to say, well, what general relativity has really done is to geometrize the gravitational field and to show us that gravity is nothing but space-time curvature, basically the modern story that you find in any textbook now. Einstein says, whoa, 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 I don't think that's what the theory says at all. You know, we use these mathematical things as tools to construct a theory of gravity, but you shouldn't mistake this as having any sort of ontological significance. A metric tensor is no more and no less geometrical than a vector as employed by Maxwell. It's the same type of animal. And so I think there is a very, coherent modern geometric interpretation of GR. I think this is an interpretation that can be defended, but it's one that Einstein explicitly opposed. He did not want to think of the theory in this way. But others did, of course, and a lot of it goes back to Weil. Yeah.
Just a very quick finger on Dennis's remark. The first actual definition of a manifold was given by Weil, right? Atlases and charts, that was given by Weil.
The famous book on the Riemannsche Flache. That's right.
I see that Jacob, Dennis, and Peter all have hands. So Jacob, let's get back to you. You'll have to unmute yourself.
Yeah, I got that. Thanks so much. So actually, it's interesting, when I first read Steven Weinberg's book on general relativity, and he takes it, and he wrote this in I think 72, and it was heavily motivated by a lot of his papers on gauge theories, on massless particles and quantum field theory in the 60s. And he takes an explicitly non-geometrical approach to general relativity, a particle physics and sort of approach. He even has a passage where he says, my views here are heterodox, but I don't regard GR as a fundamentally geometric theory, although I think that these tools are useful. I don't know, but I wonder, well, I mean, it's hard to know. I guess one could just ask him, but was he aware of Einstein's opinion here, or did he arrive at this? I mean, given his intellectual trajectory, it makes total sense that he could have arrived at this non-geometric point of view from his work on quantum field theory. But nonetheless, it's interesting that was a prominent textbook. It's one that I reference, although it's not the primary textbook I use in my course, but there's some very nice discussions in that book. And it's all the way 1972, and here's someone who's still sort of a holdout, and not regarding GR as fundamentally geometric. So that wasn't my question. My question was actually to Leo, but I guess to everybody here. I noticed that in your slide 11, which I see you still have up, the version of the Einstein field equation you've written down is what we would now call the trace reversed Einstein field equation. And I know this may be a small, maybe a trivial point, but was this the first version of the Einstein field equation that Einstein published before the more sort of standard version with the Einstein tensor bearing left-hand side? Because this is the version of the equation that maps a little more like directly onto the Newtonian limit.
Yeah, well, Norton has to answer that, but I would say that yes, because it is precisely what happens in those weeks of November leading to this. And then there is the equation. Am I right, John?
I just don't recall. I worked on this so many years ago. As we all know, the two forms are so readily transformed one into the other that it really doesn't matter which one you write down.
One important difference, though, is that the trace reversed equation explicitly depends on the dimension of space-time, right? I mean, if you work in n dimensions, you see the dimension of space showing up, it breaks down at n equals 2. Right, there is some sense in which the standard version is somehow more general and doesn't explicitly reference the number of dimensions.
You're definitely one thing. Einstein found it much easier to work with this form of the equation in order to get out the Newtonian limit, and in particular, this enabled him to get deviations from flatness in the spatial slices. Right, that was the key thing, and for Einstein, that was a big deal because he had missed that all the way through to November 1915. He did not realize that, you know, that space in the vicinity of the sun has a slight geometrical curvature, and this form of the equations lets him get that. But I'm saying Dennis has got a hand, and so Dennis might have more to say on this.
I remember when it, so the first time that the now more standard way of writing reachy tensor minus 1/2 g mu reachy scalar appears on the left hand side. The first time that he writes it like this is in 1919 in a paper that's it. The title is Do Gravitational Fields Play a Role in the Constitution of Matter? It's also the first time that he uses the Bianchi identities. So that's clearly the motivation. He has become aware of the Bianchi identities at some point, and then uses the fact that, look, if then the left-hand side, the covariant divergence of the left-hand side is identically 0, and then also the right-hand side of the now rewritten Einstein equations has to be identically 0. And then in that paper, he suggests alternative field equations in which this implication is not there, namely what we would today call the trace-free field equations or unimodular gravity equations. And contrast that explicitly with the 1915 equations in that new form.
That's very interesting.
So I have just a finger on that question. So
yeah,
I guess this is my history just being highly incomplete. But so my understanding was that one of the motivations for the correct version of the field equation, right, the improved one, the one that finally appeared before his 4th lecture at the Berlin Academy, was this problem of the lack of local conservation of the energy momentum tensor, which follows from Bianchi identities. So that was not part of the arguments that Einstein used to write down that equation. Because when we teach GR, that's one of the motivations we use for that form of the, it can't just be Ricci tensor equals stress energy tensor because so he was unaware of this. It makes it all the more incredible that he arrived at the correct equation without that important point.
Let me say a little bit about this. There was a reason that he didn't want to include that trace term. He knew that could have been added. We find versions of equations with these sorts of trace terms in his writing as early as in the Zurich notebook. But it was the key thing about the curvature of space. He thought that there were very good physical arguments for why space in the vicinity of the sun, just space, not space-time, had to be geometrically flat. And he knew that this trace term was going to mess that up. Now, the physical arguments were coming from the principle of equivalence. The principle of equivalence in Einstein's hands evolved simply a transformation to what we would now call Rindler coordinates, but are really Born uniformly accelerated coordinates. And the weird thing about them, they have this weird thing that in this accelerating frame, space remains flat. And so Einstein thinks, this is a general property of at least weak gravitational fields that aren't too fancy. Space always remains flat. And so we can sort of step through the different versions of the papers that Einstein produces in November of 1915. And you can see him slowly unwinding the physical misconceptions that had stopped him using general covariant field equations. It was not lack of mathematical ability. He had Grossman helping him. Grossman is feeding him all of the right equations. In fact, on my screen behind me, you'll see the first time that Einstein writes down. This is from the Zurich. I teach an undergraduate course, and I use this as a background sometimes. Einstein was grappling with physical problems all the way through here. And he could only finally write down this equation, the correct equation at the end, when he finally had this realization, oh my God, even in the field of the sun, space is not geometrically flat. Now contrast that with Hilbert, who is simply working on the mathematical problem. It's very clear Hilbert doesn't really have a grasp of all the physical complications that Einstein's dealing with. And so he does the simple thing that any mathematician would do. There are natural structures here. Riemann curvature tensor is the natural object. You can form a density from that. Action principles are the thing to do. Let's just vary it. We'll get a field equation out. Yeah, Hilbert is cranking the handle, right? Without a real grasp of all the physical complications that Einstein's been buried in.
However, you probably remember in the correspondence, I think after the third article or so, Hilbert is amazed about the ability of Hilbert to calculate the physical situation with the perihelion and the hydrogen atom and so on. He tells him, if I could calculate so quickly, and he refers not to the mathematical calculation or the meaning of the mathematical calculation, but to the physical meaning of what he's doing there. I don't know if he had a full grasp, but he knew he knew that this was important for Einstein.
Yeah, well, Einstein could calculate that quickly because he'd already done the calculation in the earlier theory, and we know that from the Einstein.
Well, I'm talking about the impression that Hilbert had on what Einstein was doing.
Yeah, I love that letter, by the way, because I think what Hilbert says is, and if I could calculate so quickly, blah, 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 and then the electron would have given a note of apology for not radiating. Do you remember the wording there?
Sure.
But that's a clear statement of how much, just what was happening in quantum mechanics was very present at the time. This was a real worry. Why don't atoms radiate?
And as I said, for Hilbert, this was the main thing, the structure of matter. Gravity should be or the explanation or the behavior should follow from what we know about the structure of matter.
Just a quick kind of question. To how much are vacuum solutions talked about in these papers, in these at that time? I mean, just from the modern perspective, I know it's been 100 years, but in the modern perspective, from a mathematician's perspective, vacuum is all that people do. I mean, pretty much. I mean, there's people do math a little bit, but when they couple to matter, they realize a lot of their estimates and equations just very, very hard to control. A lot of the structure's broken, et cetera, et cetera. So how much did they talk about vacuum, and how did they understand purely vacuum phenomena? Did they understand it? And was this really, did that play a role in these questions and discussions?
I don't remember any, except one very important thing, which is Schwarzschild solution that comes incredibly fast after he was in the front in the war, and after 3 months he came up with the solution in the vacuum case and so on. But other than that, I don't remember. I don't know, John or Dennis, if you remember anything of that.
I just very briefly. Well, two things. First, Einstein's long-term goal with the unified field theory was to have nothing but, in effect, vacuum solutions. Second, they weren't so bothered by this at the time, but neglecting vacuum solutions came to haunt Einstein very quickly. In 1917, he produced his Einstein universe, the cosmological model, in which he added the cosmological constant in order to get a static universe. You know the story there. And then de Sitter comes back and shows that a vacuum solution is possible for these equations. And there we have the de Sitter spacetime appearing for the first time, which of course is I hesitate to say this, but the simplest and most important cosmological solution that we have. It keeps coming back over and over again. But I saw Dennis had his hand up. So Dennis, you know more about this.
I don't think I know more, but just to complement this, I think there's an interesting, at first look, it looks a bit as if Einstein is changing what he thinks is okay, and one doesn't quite see why, because, but then it becomes clear. So when he derives the perihelion of Mercury in 1915, before he has the final version of the field equations, but the derivation just carries over, he gives with insight an approximation to the Schwarzschild solution, and then Schwarzschild a year later says, "Oh look, I found the exact counterpart of your approximative solution from a year ago." And that is clearly, I mean, in that paper of 1915, it's a vacuum solution, right? And he's explicit on that, and he says, "Well, that's what he does. I want to know the exterior gravitational field of the sun." And I think in this type of context, where he's, you know, that's for the given purpose, that's the only thing he's interested in, the exterior gravitational field of the sun. The interior just doesn't matter. I just need to know what, you know, influence Mercury feels. It's perfectly fine to work with vacuum solutions in this type of way. But the reason that he then very much dislikes the Sitter solution is because that one is not supposed to be, it's not supposed to have a restricted applicability, right? It's supposed to be a faithful representation of the way the universe could possibly be and give a more or less complete description of that. So there you're forced to interpret this as a, you know, as a solution that describes a way the universe could be. And for that, he didn't want vacuum solutions. As soon as they are, you know, it's for a region that is just the exterior gravitational field of the sun, or the gravitational wave solutions that he derives in 1916 and 1918, where you can say, well, I give the solution of waves far away from the source, and I'm not bothered with, you know, giving the material system that originally produced the wave. It's not just not what I'm interested in right now, but a proper description would, of course, have to include that, right? So in a way, he's okay with vacuum solutions for, if you want, instrumental purposes, but doesn't want to interpret them as realistic ways that the universe as a whole could be.
Yeah. I should just add the thing that both Dennis and I have skipped over because we think everyone knows this. In the 1910s, Einstein was under the sway of the Mach principle, which he formulated as saying that the space-time geometry has to be fixed completely by the matter distribution. So if there's no matter, then the Mach principle is violated and Einstein's not happy. As we all know, he later gives up the Mach principle and says it was a mistake. Never mind, it's a story, I won't go into it.
Thank you for those clarifications. Are there any other hands raised? I can't see any questions. Please go ahead.
Dennis.
Oh. Yeah, I had a question from the very beginning for Leo, which is about the letter of Einstein to Weil about Hilbert, which I always found a bit, so the way it says Hilbert is like a child and so on, I always found it a bit puzzling because, well, first of all, I'm not sure if it's in the same letter, but it's definitely a letter also from somewhere between 1916 to 1918, where he also tells off Weil in a quite similar way and says, well, the way you model matter, that's so highly idealized, it's just not a proper model of matter, right? So, and it might even be there where he compares Weil with Hilbert and puts them in the same category. But so what I wonder about, so it's Weil and Einstein don't know each other that well at the time, right? And so to write this paragraph to Weil speaking about his Doktorvater feels so highly indiscreet, and so putting Weil in such a difficult situation of how to answer to this. So I just wondered whether you could tell me a bit more about the relationship between Weil and Hilbert, especially at around this time. I know there was also the tension between Weil having strong sympathies for intuitionism and Hilbert seeing his life's work endangered. So could you tell us a bit more about their relationship?
Yeah. So you went a little bit dramatic in the end, which I think is not really the case. But do you see what the quotation now from Weil over here? So let me say a few words about this. I explicitly mentioned the Oedipal relationship between Hilbert and Weil, or more precisely, Weil towards Hilbert. This existed, and it existed already here. Now, remember also, Einstein, when he comes to Göttingen, he's still not the big Einstein. He's on the way to becoming the big Einstein, but he's not yet there. Whereas Hilbert is the great Hilbert, right? So here you have the younger person, Einstein, not so prominent. Okay, he already has an institute in Berlin, which is him alone. He doesn't have a Nobel Prize. He has the 1919 episode, with in Britain. So nothing of this exists. So it's a kind of peregrination of Einstein coming to visit the big Hilbert. And I didn't stress very much this asymmetry, but there is an asymmetry here, But one has to say that Hilbert was very open to young people. I mean, it's not a matter, he was in this sense not very typical of German professors of the time. He was very open to listen to them, and he was really, he knew how to appreciate the work of the younger people and stimulated them and so on. So I would say, it's true what you said about indiscrete, I don't know, but in this sense, Einstein is closer to Weil in age, in prominence, in whatever you want to say, and apparently also in scientific ideas. Einstein and Hilbert, on the other hand, became very close also, I would say, I don't know if I can say in their political ideas, but certainly in the way that they approach German society. And, you know, all the status of the professor and so on. Hilbert was not typical in this kind of thing. There is the story about Eminetter, you know, that there's this nicht eine Badeanstalt and so on. So it's an interesting triangle, but not a symmetrical one. And Hilbert is up, and they now the tension that you mentioned between Hilbert and Weil around intuitionism starts a little bit later than this. This is 1915, and that reached a peak in 1919, let's say. So that particular tension didn't exist. And I don't agree that this is a different talk that we can say one day, that the intuitionism was trying to destroy or could destroy, in his view, Hilbert's work. Remember, this has to do with this idea that Hilbert as a formalist. This is just one important, but just one point in his career. Like he treated integral equation, infinite matrices, and then there is the question of the foundations of arithmetic. That's all. I mean, it's important, but this is not his life, even though it's called the Hilbert program, possibly wrongly so. But that's a topic for a different discussion. Now, you see here in this quotation, I don't remember. I just was looking at this other presentation today, but I can find out exactly when this quotation is from. But you see that Weil, in this sense, was closer to the view of the physicists than Hilbert was. I said Hilbert was very much interested in so on, but from a very mathematical perspective. We just spoke about this. And Weil, who was also a very strong mathematician, also working in, in the classical fields and so on, but he seemed to have had a closer connection, let's say, or intuition about physical things. And so I don't know when this relationship between Weil and Einstein arose, that Einstein thought that he can say something like that, but obviously it was there in some way.
Thank you. Just to say, it's interesting that the presentation of intuitionism challenging Hilbert's life's work, that I had that from Born, right? So when Born in the whole fight over the leadership in the Mathematische Annalen in the second half of the 20s, tries to convince Einstein to side with Hilbert and so on. That's how he presents it, right? He dramatized.
No, I mean, Hilbert was upset about Brouwer and all of that, but he couldn't think that this thing is going to pose a problem for his work life. I mean, no, I don't believe so. And even not for some of his views about the foundation. He thought that it was wrong. That's what he thought, that is purely wrong.
Right. Thank you.
I see that John has a raised hand.
So, Leo, I'm a little afraid to ask this question, but I'll go ahead and ask it anyway. So I understand that Hilbert was a Kantian. Is that correct? And did it express itself in the work that we're discussing in any way? I mean, in my view, after you know that geometry is not Euclidean, it takes some dedication to be a Kantian.
No, why sometimes there is this talk about Hilbert being Kantian? In the Grundlagen der Geometrie, I don't remember exactly the quotation, but there is a quotation about from Kant saying intuition without empiricism. I don't know. Why does he write this? I think the reason is completely different. there was the great Königsberger, that was Kant, right? He was the great son of the city of Königsberg. And then there is the second big son of the city of Königsberg. This is Hilbert. But when he wrote this, he was not yet that big. He was the racing star. This is 1900. So I think that he thought it's very elegant, you know, to put this quotation of Kant over there. And then people have, I think people have made of it much more than there is. Now, it is true that sometimes here, I say, you know, Hilbert at this time concerning geometry, he is empiricist. This is what he is. I mean, you are better at those things than me, but I think that if you come and look at his work with these perspectives, and you know, you see it everywhere. And I'll tell you another thing. I think that Hilbert was not that much of a philosopher. Not that he was ignorant of philosophy, or, you know, I think we have had similar discussions about Einstein. You know, the people, well, he appeared in the philosopher's library of our time and so on. So he suddenly becomes a philosopher. You know, a philosopher, you are a philosopher. You have to sit down and write philosophy. It's not just a matter of, you know, I have this idea or that idea. Like a physicist had to sit down and do his physics, and a mathematician, things don't work that easy. He sometimes speaks about things like that, but I think that this is not really an important topic. It is an interesting, you know, he got the honorary citizenship of Königsberg in 1930, 29, precisely the day, you know, that Gödel was announcing his theorem that also supposedly destroys his program. This is another dramatization, even though it is true, the very same. So Kant, Hilbert, Königsberg, there is a strong symbolic load around this. I don't think this is very important.
All right. Well, that was a pretty definitive response. Anybody else would like to?
I had a very quick question. Again, this may be a very naive question. Sure. You talk about Mie's ether theory with matter appearing, the electron being a singularity in the ether field. What was the status of the ether at this time? I mean,
it's a good question, because the question is good because usually we say, okay, special relativity, Einstein eliminates the ether, right? This is what I think John Wilson spoke about this one time in the past, and I see ether coming again and again, and it appears elsewhere. So in other words, ether as such, it didn't disappear. I think it changes status, but it didn't disappear. Right.
I mean, Dirac is writing about ether theories well into the mid 20th century. But you know, in Max Born's autobiography, you know, of course, he's writing during World War II, but he writes about the time of the early 1900s, before 1910, or shortly thereafter. That he writes as if the ether had already been completely banished from polite society by that time, but clearly, you know, Mie was still building models out of it. So it's just very interesting to see different people talking about this and having a different understanding of how. Yeah. I mean, was this view? I mean, obviously Hilbert was thinking about this to some degree, but was this view widespread in physics, or was it more of just the math community?
Well, probably John and Dennis can say better, but I saw it appearing in many places, surprisingly. For me, it was a surprise, but I don't know.
I think I agree. And I think one thing one has to look out for is that different authors, especially after 1905, may completely change the meaning of the term ether. Sometimes they explicitly say so, and sometimes they just do it. And so, I mean, even Einstein gives a lecture in Leiden in 1920. Well, one has to be careful. I mean, the words that he chose clearly were also there to pay homage to Lorentz, right, who he admired above everybody else and who was the man in Leiden. But I think, I mean, he wouldn't have said it if he didn't mean it to some extent. He meant, well, you know, So to some extent, we didn't need the ether anymore for special relativity, but in some sense, G mu nu in general relativity, that's the new ether. And it's a perfect, and that's him saying, now it's perfectly fine to call G mu nu the new ether. In many ways, it does the type of thing that before we attributed to the old ether. And and at some point, I think, well, maybe as a result of this, so many people sort of switch around with what the term refers to, that it fades away, but, and it's just not being used anymore because it has become too manifold in meaning, maybe, but
it doesn't die in 1905.
no.
Right.
You know, from a shot into the head. No.
But also, like in the 19th century, it had a very, a more or less concrete. It was a substance. It had mechanical properties. And Born in his autobiography, he says that physicists felt they understood its properties better than the properties of ordinary matter by the time special relativity came around. What was meant by it? Did it have even one meaning after that point? Because clearly, was it understood? Like, was there a consensus that if people worked with it, it should be understood as some kind of Lorentz invariant substance? Like, what did they mean by it after relativity came into the story? Special relativity, I mean. Like, what did ether refer to?
I'll say a few things here. First, what does the term ether refer to? The idea is that electric and magnetic fields are states of something, and that's the ether. They're states of the ether. Maxwell had a very powerful argument for that to do with interference. The effect of interference is that two waves can come together and they can annihilate. So how can two independent forms of matter annihilate completely? Well, Maxwell says it's because they are states of something else, and we are looking at displacements in opposite directions. And you can understand that in a very, very general term, and then you can still see there's a place for an ether. The key thing about what Einstein did in 1905, when you read very carefully, what he's actually succeeded in doing is showing that if there is an ether, you can't attribute a state of rest to it. But that doesn't preclude the possibility that electric and magnetic fields are still properties of something. It doesn't even preclude that today, right? Now, the idea of the ether then just continues on. I mean, there's tremendous inertia here. You've got a whole community of physicists, all of whose lives are devoted to ether physics. And they're not suddenly going to say, oh, yeah, I guess you're right. Well, you don't need that. Lorentz at the time was the great figure, the leading figure, and he was not convinced by Einstein. And this is clear in publications. Again, Dennis, you might remember this, but I think, isn't there a correspondence between Einstein and Lorentz in 1916 where Lorentz is hanging in there and they're just going backwards and forwards? Einstein's trying to convince Lorentz, and Lorentz is hanging on to the ether.
And in a very informed way, right? I mean, Lorentz writes four long papers on general relativity in 1916, really going into the details. I mean, really, Michael Janssen wrote about this in detail, to some extent, giving the first, properly generally covariant presentation of the whole thing, and really, doing something important for the mathematical presentation of general relativity. So he's not just hanging on, but are you sure that one can't interpret whatever you're doing in a way that is consistent with ether? No, he really engages more deeply than most others with general relativity, and says, oh, well, that works. I mean, it still fits in a new way, but it doesn't in any way prove that the ether doesn't exist. It's just that, yet again, as Lorentz himself did before, change the attribution of what properties the ether has. And what
at some level, like, a space-time without an electromagnetic field at all is different from a space-time with an electromagnetic field in its rest state, right? When we teach electromagnetism, we don't talk about electromagnetic waves as being waves of nothing. We teach our students there are degrees of freedom at all points in space, and they can be excited, and these are, so I mean, there's a sense in which we're still working with an ether-like concept, but one that's sort of a Lorentz invariant kind of concept. So I guess that makes sense. It's interesting that when you look at skyrmions, right? When you look at topologically non-trivial states of certain non-abelian gauge fields, there's this effective low energy theory, that the pion-Lagrangian theory of mesons, that protons and neutrons and other baryons can be understood as topologically non-trivial states of a field, in a way that's kind of reminiscent of the knots of the old ether theory. So I guess there's a sense in which the idea has kind of evolved, but hasn't quite disappeared. Anyway, this was a wonderful talk, Leo. I wanted to thank you. This was incredibly helpful. This will change how I explain the story when I teach the class. Thank you so much, and thanks everybody. I gotta go.
You were a great audience, really. That is very unusual. I'm glad. Thank you very much. Hope to see you soon. I'm glad to know those whom I didn't know before. John, to see you after so many years. And hopefully we will meet in person sometime soon. This is becoming very Martin, thank you for the invitation.
Thank you very much. Thanks everyone for joining. A wonderful discussion.
May I ask, is there a way to get, Leo, is there a way you could share your slides? There's a lot of really great stuff in there.
No problem. I think I have your email or...
Oh, and also, I don't know if anyone saw Peter's note, but he just wanted did everyone see Peter's note in the chat? That everyone should sign up for so if you haven't signed up for this group seminar, you should do so.
Yeah, do let me know.
See what he says. Okay, I didn't see it. Okay, good. And I can share the slides, of course. And I'll tell you more. You can go into my website, just write Leo Corry on Google. All my articles are there. The book has many of these that is not in the article, but the book, I always say, don't buy the book. These people take 170 euro for a book, but this is crazy. But I'm sure you have it over there in the library in Harvard, and you can browse. You can read a little bit about me, about the details. I forgot many of this. I did all of this a long time ago. I have a good memory, but not that good. So I had to today to reread some of the details.
Great. Well, thank you very much. The talk has been recorded, the questions as well. So it'll go on YouTube. So you'll be able to find that. And thanks everyone for joining. And thank you again, Leo, for a beautiful, beautiful session.
Thank you. Bye-bye.
Bye-bye, everyone.